Okay, in the interest of time, I'm gonna ask someone any interesting things that you would do.
They have this beat that is like the blackest you know, it scores like 95% like it's, I don't know if they're using that also.
Yeah, that's a good point. One of the big problems, of course, is that you don't want the heat to escape from the system. You want to absorb as much as possible. And what's your name?
Sorry,
Andrew is saying that if we can, and you are saying that if we can have really well-engineered paint or some material, carbon black is what I remember. I think there's also a form of diamond where folks are doing it. This is a very important point, not only for solar cookers, by the way, and I will talk about this for light trapping in solar cells. You can do the exact same thing for solar cells. You want to absorb as much light as possible. You want your solar device to look like a black hole. You don't want the light to escape, right? It's a good point. Any other crazy ideas? Feel free to shout out. Yeah, Amrita. Mm-hmm. Yeah, okay, so let me repeat that. So what Amartya is saying that if we could allow, so actually let me go back to this example here, maybe that's easier to see. If we design an enclosure such that we allow as much of the light to come in from sunlight based on the spectrum of sunlight, which we'll talk about, and of course the black body in there is absorbing this based on your technology, let's say. But as the black body heats up, we know from basic quantum mechanics, which you hopefully all learned in high school physics, that it will also radiate. It will radiate at a wavelength which depends on its temperature, which is a lot shorter, a lot longer than the wavelength it absorbed in. This comes from Planck's formula in basic quantum mechanics. What does that mean? The absorbed light is at a short wavelength, radiated light is at a long wavelength that allows you to design this enclosure to prevent the long wavelength from escaping. Now, you mentioned something else about water. The problem with water is that water vapor is highly corrosive. It's a huge problem that people deal with. It's an interesting problem for some team to address. Because when you cook something, you create a lot of water vapor. Creates a very humid atmosphere in here. And that will corrode whatever is here and it'll destroy it. Right? What do you do about it? Okay, great. I was happy. Yeah, do you want to read it? Or yeah, let me read it so it's recorded. Jared, so I have a simple circuit. One problem I see is they don't retain heat when sun goes away. That's a very important point. So have a simple circuit detect it when it stops getting sunlight and have an insulator close to keep the heat. Yeah, excellent point. And we'll talk more about it. That's a good point, of course, because sometimes you want to cook your dinner and eat it after the sun goes down, right? What do you do? Thanks, Jared. Oops. I'll also talk about a couple more types of cookers. So first of all, I was just going to say I was excited to hear all the noise. So that means at least you're talking. So that's good. Keep that up. We'll do a lot more of this, more complicated things. We can also have a Fresnel lens cooker. So this is Fresnel lenses, for those of you who may not know. If you open up an old TV, this is what you see, and that's simply a lens. The big lens, it's really flat and thin, lightweight. You can use it to start fires, just like the parabolic cooker. Pretty dangerous. So, okay, let's talk briefly about the heat principles in the last 10 minutes or so. We need to understand some of this as we think about these problems. Again, my goal here is not necessarily to emphasize solar cookers to all the groups, but I want to give you the steps to think about the problems and how you will approach it and how you will solve it. With this as an example. Okay, that's my goal. So heat gain, how does it in heat? This is by the greenhouse effect that we just talked about. Visible light passes through the glass, is absorbed by the dark part, right? This is a black body. It's going to re-radiate at a longer wavelength. That longer wavelengths will be at infrared wavelengths, which will be trapped by the transparent cover on the top. So this design of this transparent cover on the top is important. It should allow the visible light to pass through, but prevent the longer wavelengths from passing through. And it should, of course, not absorb any light, right? You don't want heat to absorb the light. If it absorbs light, it simply heats up, and that's a waste of energy. Secondly, and that's what happens in the system. So think about this, the closed system. That's how you gain the heat in the system. And the absorbed energy from this black body must be conducted very efficiently to the food that's inside. Okay. We can also do interesting things to improve the heat gain, the orientation of the glass. So we have two examples here. You have a box 1, right, coming in direction, a box 2. Let's see if we can answer this question. Which box will receive more sunlight? And you can just shout out. Yeah. And now one way to think about it is, of course, we need to think about the plane of intersection, right? So this is the aperture of this. Actually, I should probably use this, sorry. This is the aperture, and the light's coming in at an angle. So we need to project the aperture such that it's normal to the light. So there's a theta here. So this aperture is A, this becomes A times cos theta. Right? So that is the effective aperture that the light sees relative to the entrance of the cooker. And we'll talk more about it when we talk about solar concentrators. Now, the fact that we increase this side means that now you're collecting more of the light, and now you can see the aperture here is larger. Right? Of course, you can calculate how much larger and so on. Now let's see if we can answer the second question. Which box has more losses? Someone said box 2. Anyone disagree? It's okay to be wrong, by the way. It's good to be wrong because that's how you learn. So don't feel bad or be shy, I suppose. Yeah, so it depends on what the loss is, and we haven't talked about it. But the thing about the box 2 is that it has larger surface area, right? It has all this, yeah. You have this part which doesn't exist in the other box. And surface area is good and bad. It's good as the first step because you're collecting more light, but it's bad because you're going to re-radiate the energy out. So there will be radiation losses. Now, of course, I told you that the cover should prevent radiation from escaping, but of course, it's not perfect. It always has losses, right? So one would expect box 2 to have a higher losses as well. So this is why it's important to think about the gain and the loss. So whenever we do something, we also have to think about unintended consequences to some extent. Very simple example here, of course. And thanks, Jared, you're right. Let's see. We can have reflectors as we saw before, right? So you can increase the effective light capture area. You can have a reflector on one side as we saw in that photograph of the cooker before. You can have a reflector on 2 sides. Now we're going to do one more brainstorming session.